All right, so this is lecture 20. We are starting the section 4, which we will focus on other advanced supervised classifier. And the first advanced supervised classifier we will cover is support vector machine. And this is the module 1 of support vector machine. And we are in the discriminative classifier group. We have finished cover the generative and instance-based classifier groups. And after support vector machine, we will cover decision trees. Okay, so let's get started.
So just to summarize, again, we are using the nutshell to summarize. So the major tasks support vector, this type of machine are used for classification, but it actually can be used for regression too. And the representation is something called kernel trick. And this kernel trick is extremely powerful, but you actually already learned it. The whole idea behind the kernel trick is related to the basis function we used to expand linear regression to the nonlinear cases through the basis function expansion. And this is really just that phi x, and you just need to design it. But here, there's a little bit more trick, a different formulation from those basis function representation into something called kernel function. It's actually extremely simple. It's just an inner product of the phi x versus phi z. So what you actually use is not directly the phi x, that expanded representation you actually coded in your homework 2, like in the polynomial case. What you actually use is the inner product of a sample, maybe sample x, and inner product with the other sample z's, that phi representation. You're using this inner product of, you can call that similarity measure directly. So we're going to talk about why we do so and later, but this is a very classic trick called kernel trick. And the loss function is also slightly different from what we learned before, because everything we learned before is squared error, right? It's all squared error. In the k-nearest neighbor case, I did not even cover what we're optimizing. So I covered a little bit about expected prediction error, but to prove what is k-nearest neighbor minimizing, there's a lot of probability behind, so I moved all those proofs into this extra in the k-nearest neighbor section. If you are interested, you should read it. So in fact, k-nearest neighbor minimizing the expected prediction error when using the L2 loss. Again, it's still a L2 loss formulation. If you use L2 loss inside expected prediction error, and the best prediction at each point is the conditional mean. And k-nearest neighbor is exactly an approximated version to estimate conditional mean. So at the current point, what is the conditional, what is the point, what is the probability, what is the mean probability of y? That's exactly what you did doing majority voting. So if you're interested, please read that extra lecture. Its idea is expected prediction error plus L2 loss, and then the solution is conditional mean. K-nearest neighbor is giving you the approximated conditional mean solution. But everything we covered before, it's all using the L2 loss, right? It's the y minus fx take quadratic, right? It's always L2 loss. It's summation of whatever I from 1 to p, well, actually not p, so it's the true y minus the fx take quadratic, and this is one sample. When you have n different samples, you just sum over all the samples. if you take the mean, this is an empirical estimation of the expected prediction error actually on the training data. So, but anyway, so now we move to the first different method using not L2 loss anymore. So this is something called margin plus actually hinge loss. And the formulation we had before, we always use gradient descent to solve it, and or using the analytic solution like normal equation. In the famous neighbor, we don't even solve it, right? We just directly use majority vote. And the reason is that majority vote is approximate conditional mean. It's truly solved that L2 in the expected error formulation. But in SVM, it's a different formulation, and we're going to introduce some idea called quadratic programming. But quadratic programming in this raw form, the raw form is, we're going to talk about it, and there's, to make it more efficient, people actually truly solve the support vector machine using something called dual form. And it's about quadratic programming reformulation. And in the end, your weights. So in the old days, we always write our weights is fx equals to W transpose x, and in class buyers. And when we learned everything before in the regression case, we would directly solve W and B. However, in the SVM case, because its dual form is more efficient, we truly solve the parameter got a reformulation into something called the Lagrangian or dual form of parameter. It's called alpha. So this is really too much, I understand, but I want to give you overall a rough, quick review. And then later, we're going to cover each one of this slowly. We're going to cover the margin and margin formulation today. And then we're going to also cover why this is a quadratic programming. So hopefully next lesson, we're going to cover the dual form and how do you solve the dual form, and why to solve the dual form. How the dual form related to the margin definition of SVM. So this is the primer formulation, and this is the dual formulation. And this is the scoring function we saw in the SVM. It's just too tight for me to move it to here. So this is the optimization formulation. And today, my main goal is to actually tell you a simplified version why this formulation makes sense, why we're using such kind of scoring goals to optimize towards to learn the parameters. All right, so this is because SVM is a actually pretty complicated and also math-heavy classifier. So I just decompose the topics into all this variation related topics. So today we start from the histories, and then until the end of this class, I hope I can cover until here. And the next lesson, we're going to cover the rest of the three or two, actually maybe only two topics, because the middle two are extremely math heavy. It's the Wednesday class. Okay, so if you attended my talk yesterday, I tried to give an overview about AI and CSAI. So I found it really refreshing to understand history. And then history really tells us why now? And maybe it tells us something about future. So what is the history of SVM? So SVM is a very, like I said, it's a very statistical learning theorem grounded design. It was first introduced in the early 1990s, and SVM became very popular because its success in handwritten digital recognition in 1994. So you might feel kind of, wow, such a bad result for now, but at that time, it's a truly breakthrough. It's kind of beats LearnNet. It was actually one of the older multi-layer perceptron. It's better, very solidly on this very smaller data set. We think it's small now, but it's the largest data sets at that time. And because of this solid winning, and people started to realize its performance, realize its importance, realize its the potential applications this method can be applied for. So there are a series of papers actually compare or analyze the SVM, and these are the 3 papers. And Volap and Vapnik is the person who created SVM, and then there's a lot of continuous work. And this is almost the hottest topic in the about like 1995 to maybe 2005. So what is MNIST? So I think a lot of you already know. It's really just you collect a lot of people's handwritten digits and you try to classify them into 0, 1, 2, 3, 4, on to 9. It's classified into this 10 different digits classification task. It's a small, tiny image. It's pretty large at the 1990s. So at that time, nearest neighbor got about like testing error about 2.4. This multi-layer perceptron, it's 1.6. There's all this various version from Yang Kang actually doing this variations of multi-layer perceptron. Now you might feel, why do you even do this, all this smaller detailed that number of, and then the middle number of hidden layers, and then how many hidden layers, how many hidden points in each layer. In fact, it's actually extremely hard to train those multi-layer perceptrons at that time. There are no shared big platforms, and people just code everything from start, and then extremely hard to tune, extremely hard to control its performance, extremely hard to know what's the right architecture. So SVM, I mean, you don't even need to do much of the feature engineering. It actually achieved better results than one of the best multi-layer perceptron network called the LearnNet 4. And then starting from there, and then people started to use it in many, many different applications. And because of it's theoretically grounded, it provides very solid results. And it's not that difficult to tune it, and there are not a lot of bolts and knots. You know, in the neural nets, you need to figure out what's the number of layers, what's type of layers, how many layers in how many cells in each layer, and how do you use whatever gradient descent approach to tune it, and the mini batch size and learning rate. You know, there's just so complicated at that time because there's a lack of good computer hardware support, and also a lack of good platform software and library platforms. And SVM, it's much easier to use toolboxes. And it's not very sensitive to a lot of parameter tuning. I mean, it's extremely stable. There's only one parameter you need to tune, which you're going to code it in the homework to tune that parameter to see what's the performance. I can even tell you now, performance, no matter whatever this different kernel you try, like is very stable. The results, it's kind of stable, very, very stable. It's more like, it's not very much with the large range of parameters. So, which is a really good thing if you think about it. When you don't have that many of training samples, and a stable performance, robust performance is really what you want, right? So that's the reason why SVM becomes very, very popular before the deep learning, the whole hype of deep learning. It's stable and it's powerful. It gives solid baseline results. So because we're in the deep learning era, so I want to again to review and how did all those up and down of different methods happen and why. So I actually had part of this slides yesterday, and also I have part of the slides in our first lecture, but I still want to review because this SVM and deep learning, and also some of those methods we don't cover, like a graphical models, structure prediction, and they're all really important toolboxes, and why sometimes this method becomes more dominant, why sometimes the other method becomes maybe less dominant. So we know the Alan Turing defined the problem, defined the task. Can machine? What's the relationship of machinery and intelligence? He proposed this famous Turing test about if you want to know if a machine is intelligent, there should be a test to trying to have a human input and then a computer input, and these tests should not be able to distinguish the computer input and the human input. If this test is solidly tested, we actually can prove, and this is a test to prove, this computer algorithm reached the intelligent level. This is a famous Turing test, and you can actually tell there's a lot of flavor. The state-of-the-art generative adversary network uses the idea. So there are a lot of history if you go back to think about it, and it can guide you to think about future, right? I mean, in Goodfellow, who invented the generative adversary network, exactly uses the Turing test and formulated, even though people now talk about like a game theory or whatever, but the more deeper root is from the Turing test. Okay, so that's the first thing. And then the AI was defined in 1956. And the machine learning, most people actually have the shared view about the invention or the first work of machine learning, or to be honest, more like data-driven AI program, is from the Samuel's check player. He just collected a lot of past check playing pairs about win or lose and all this, and he's using this past historical playing data to write a checker program. Most people treat that as the starting of machine learning inside the AI. And then in the deep neural nets, or maybe the earlier version of neural nets, multilayer perceptron, was actually invented in 1952. And there was a lot of work in the 50s and 60s doing all this crazy type of neural nets. However, all those hype, there was a hype by then in the 60s, kind of cool down and go to the winter stage. Is just so difficult to train this type of model, and so hard to control, and it's so sensitive to whatever noise in your data. And then starting in the 70s, the expert system, which some people think they are more AI, and we normally call expert-based system plus the knowledge bases are the AI systems. But in fact, it's just, if you look at the history, the whole history of AI is just when there are some maybe 50s, 60s, more data-driven neural nets, model-driven dominating. And then later in the 70s, 80s, it's more knowledge bases, rule-based dominating. And then in the 80s, the decision tree, more advanced decision tree starts to dominate. But this is still within that category of expert system, because expert system in the end, it's a rule-based or logic-based formulation. Then in the 90s, so the thing so popular now, reinforcement learning, was actually invented in the 1990s. And convolutional neural nets, recurrent neural nets, which we call them now as deep learning, was all invented in 1990s. And also there's some really important work of BaseNet. It was invented in 1990s, and also boosting, ensemble of trees, stacking. If you ever attending the Kaggle competition, actually the recent winners are mostly based on some idea called this ensemble of trees, or the boost XG boost idea. It's a combination actually from, I'm going to talk about it, XG boost it's very similar to the current hype of deep learning. It's a combination of computer architecture, because it uses really efficient multi-threading structure, plus the boosting idea from basic machine learning or a statistic, plus good data, good amount of data. And sprawl vector machine dominating in the 2000s, but it's invented in 1990s. And then later, the graphical model dominated in 2000. So back in the days when I did my PhD, it's all about graphical models. And we don't even learn much about all of this neural nets at all. And that was the winter time of neural nets, it's 2000 to 2010. So SVM is invented here, but it's got really popular in the 2000s. So the reason why I'm doing this historical review is because I want to, just don't think about all the things I invented now. There's always a lag of about 10 or 20 years. And normally the theoretical grounded work has shorter lagging time, lag time. The more heuristic-driven work has a longer lagging time, like deep neural nets. So, you all know this ImageNet competition. That's the reason why and the deep learning hype started. And I don't want to talk about it again, but because we're going to cover this in deep learning, so now it reaches almost a human performance used for the object recognition task. So, and then there's a lot of breakthrough from 2013 until now. I mean, again, the deep reinforcement learning, neural networks. However, if you look at the history I just reviewed, the CNN model, to be honest, is exactly this 2013 thing breakthrough. CNN and RN was invented in 1990. And deep reinforcement learning was invented. It's not deep, but reinforcement learning, it's 1992, but now it got this rebirth in the 2010s. And actually, again, the only thing truly is invented now is the GAN model, I think. All right, so what's the reason why? I had the slides yesterday, but I just want to repeat it. So the breakthrough of deep learning is because, it's not because of algorithm. But of course, GAN is a novel algorithm, and that's the algorithm breakthrough. But in general, the deep learning breakthrough is about plenty of labeled data. The other thing is the computer architectures, the GPU card, graphics, processing units card, actually got adapted into deep learning, make the parallelized computation feasible. And the deep learning models are so huge, humongous, right? It really needs to make use of the computer architectures to parallelize the operation as many as we can. Otherwise, there's no way you finish even training a smaller network. That was the reason why in the 1990s, even though all those networks you actually can, it's a very flexible model. You can just create whatever big models, but there's no way you train it. So similar to this breakthrough, first is deep learning. There's another, maybe you know, called XGBoost. And this really fantastic method recently won almost all the Kaggle prediction competitions. It's kind of follows some similar path. It has a good library. This author created a really good library. It also makes use of the current state-of-art advanced computer architectures very nicely in the algorithm design. So question about this? I know you like this topic, so that's why, even though I'm talking about SVM, I still have a little bit deep learning here. But the reason is I want to let you understand better, how do we reach the current point? Okay, yeah, so in fact, I want to ask you a question, just roughly. So we talk about bias and variance, and deep learning is actually, I haven't covered it, but it's a really, really, really complicated model in most cases. What is the potential issue of deep learning from the bias and variance trade-off perspective? Is it have high bias? It's because it's so complex, right? It's a low bias model. And normally when it's low bias, is the coupled side of variance is high variance model, right? So we haven't covered the trees, and the XGBoost is really an ensemble of trees, which I'm going to cover later. Tree type of model or decision tree is also extremely important method got popular in the 1980s, but now it got this rebirth from XGBoost. It's a model, is the tree based, and when it's tree based, it normally has the high variance too. It's a very extremely high variance model. And then the XGBoost really got using something ensemble method to reduce its variance. So the design of XGBoost in the beginning is to how do we reduce the variance? And when we have such a low bias, high variance model, and how do you reduce the variance? It's also a pretty nicely theoretically grounded design. All right, so this is more like bigger picture. And now let's start to do the SVM, which seems to be a vintage. For some of you, maybe this is so vintage topic, but it's a truly important work. So, all right, so basic simple vector machine classifier is for classification, and also the classification labels are quite specific. It's -1 and 1. This is designed actually just is you have to have -1 and 1 labels for the binary for the SVM classification. And we're going to talk about why. It's very easy, you can tell why it's -1 and 1. So its basic task is binary classification. It's in the first lecture, we're trying to see what is the binary classification, right? So we have two groups of points. One is this black point, the other is the empty circles, the black circle versus empty circles, and they're clearly can be separated, and the simple separation can be just a line. But the issue is, and right in the first class we talked, means there are just so many possible lines to separate the two classes. You can put it here, there, and there are just so many possible kinds. And how do you design some kind of strategies and to figure out a good separation? So then the idea behind is rather than fit a line, I'm fitting a band with some kind of wideness property. The wider, the better. So in the end, I'm looking for those separation band, separation regions. And then the wider the region, the better. So I'm looking for the region, that band region, separation region, achieved the maximal wideness. So the wideness, it's actually defined as something called margin. The margin of a linear classifier is the width that the boundary could be increased by before hitting a data point in your training data. So this is the definition of margin. It's you actually can fit multiple different regions too, right? Different when you change the slope, that the wideness actually varies. This is another possibility. So the orange one is one, and the red one I draw is another possible region. And then the whole point is I want to find the region with the maximal width. And this is called max margin linear classifier. And this is the simplest kind of support vector machine, which is called a linear support vector machine. So then you're going to have the question is, so why it's called support vector machine, right? It's all about those points that my margin hit within the training data. The points right being hit are the points called support vectors, because they are a vector representation in the high dimensional case, right? Each data point is a vector. This is called support point. They are called support vectors. So because we know the linear classifier, if you remember, how do we represent the linear classifier? So whatever linear line in this p-dimensional space can be represented as, I think I have a page summarizes. So yeah, I already talked about the region. So the whole idea of support vector machine is, so rather than focusing on all the points, I'm focusing only on boundary points. And I'm learning a boundary leads to the max margin, like I said. And those points are called support vectors. And this margin is the one of the goal I need to maximize. So why maximize margin? Because intuitively, it makes sense, right? The reason is it gives you this safe, very safe boundaries. So if you have all those flexible, the other all possible lines, the uncertainties is actually pretty large. While you have max margins, you almost reaches the maximal certainties of in the middle, I do not know. On two sides, I absolutely sure. And this intuitively making sense. The middle, I do not know much. They are the flexible region. On the two sides, I'm absolutely sure one side is +1, the other side is -1. This has very good theoretical empirical results supported by many, many different applications. And also you can actually prove it through some theorem called VC dimension we're going to cover in the third class of SVM. Okay, so I already covered this because they are called support vectors, so that's why this is called support vector machine. And then the question is, how do you learn that region? And how do you even represent that region, the band?
Great, so this is the end of this module. See you in next module.